So the main theorem that we proved in the previous lecture was that to check if a subspace of Rn is compact, it's enough to check that the subspace is closed and bounded, and as an application of this we proved that SON is compact. So in the previous lecture we proved that a subspace Y of Rn is compact if and only if Y is closed and bounded. Right? And as an application, we saw that SON is compact. Right. Similarly, we can prove that ON, UN, SUN are compact. So slight modifications of the proof that SON is compact will show us that ON, the group of unitary matrices and special unitary matrices, these are all compact. Okay. So today we will, in this lecture, we will first study how compactness behaves with respect to continuous maps. So let's begin with this proposition. Okay, so let me just write that. So behavior of compactness with respect to continuous maps. So we begin with this proposition. Let f from x to y be a continuous map right. So the image of a compact set, of a compact subset, is compact. Okay, so let's prove this. So let Z contained in X be compact. So then we need to show that f of Z is compact. Okay. So let us assume that so let me make a remark. To show that f of Z, or rather a subspace is compact, it is enough to show that if y prime is contained in a cover ui, where ui is open in y, then y prime is contained in a finite cover. So we have seen this already on 2 occasions before. So let's just prove this. This is easy. So suppose y prime is compact. Right, and y prime, we are given that y prime is contained in this in this cover ui's. So this implies that y prime is equal to, this is an open cover for y primes, right? And since y prime is compact, so this implies that y prime is equal to, there's a finite indexing set uij, which implies that y prime is contained in union uij, right? Conversely, suppose y prime has this property. Conversely, suppose y prime has the above property, has the property that if we put y prime, if y prime is contained in an open cover where ui's are open subsets of y and not of y prime, then it is contained in a finite subcover. Then let us show that we show that y prime is compact as follows, right? First, let us take, let y prime be equal to union I in I, wi be an open cover of y prime. Now y prime has a subspace topology, which means that each wi is equal to y prime intersected ui for some ui open in y, right? So this implies that y prime is contained in union I in I ui, which implies that it is contained in, because it has this property uij, which implies that y prime is equal to j equal to 1 to n w. This implies y prime is compact, right? So we will repeatedly use this remark. So if we want to show that a subspace is compact, we will show that every time it is contained in an open cover, it's contained in a finite subcover of that open cover, right? So we need, in our case, we need to show that f of z is compact. So suppose f of z is contained in an arbitrary union, let's say vi's, where vi is open in y, right? So then we have z is contained in this cover I in I, f inverse of vi, and since f is continuous, this is open in x, yeah? And as z is compact, there is a finite set, so z is contained in ij, which implies f of z is contained in vij. Thus f of z is compact. So this completes the proof of the proposition. Okay, and we will prove the following lemma. So the following proposition is very useful. Is very useful. Proposition let f from x to y be a bijective continuous map if x is compact, then f is a homeomorphism. Okay, so proof. So, to show that F is a homeomorphism, it is enough to show so since F is bijective and continuous, yeah, it is enough to show that the image of an open subset is open, right, and which happens if and only if the image, that is an easy check and I leave it to you, of a closed subset is closed. Yeah. So, we will show this, right. So, let Z contained in X be a closed subset, then as X is compact, this implies Z is compact. This is because we had proved that closed subspace of a compact space is compact, which implies that F of Z is compact, which implies that. So, once again we are under the hypothesis that all our spaces are Hausdorff. So, in a Hausdorff space, a compact subspace is closed. Right. So, F is a bijective continuous map and it takes closed sets to closed sets. From this we can easily conclude that it takes open sets to open sets. So, or in any case from this we easily conclude that F is a homeomorphism. Okay. So, before we start a discussion on, so this was a very general discussion on compactness, and before we start a discussion on compact metric spaces, how compactness, how we can, so just as earlier in case of metric spaces we had given a special description of closed subspaces, how we had explained how to describe closed subspaces and how to describe continuous maps between metric spaces. So, in case of compactness also we can make some comments when our space is a metric space. But before we go on to that, we will state this following very important theorem which we will not prove. Let Xi be compact topological spaces for I in I. So, this capital I is now an infinite, possibly infinite index set. Then this product Xi, obviously this is being given the product topology, is compact. So, this is called Tikhonov's theorem. And we will not prove this in this. Yeah, a proof may be found in Munkres. So, we will end this lecture here.